So far we have the following parts of the Tonti diagram. The displacement, which has components in the x and y directions. The strain, which has the three components, epsilon xx, epsilon yy, gamma xy. Stress with three components. And the external force per unit area with the x and y components. Strain is related to stress by this matrix of derivatives, which we call B. Stress is related to strain by the constitutive matrix. The question is, how is stress related to the external forces? And that's related by equilibrium. So to find out what that relationship is, one idea is to use virtual work, another idea is to use equilibrium directly, and a third idea is to guess from our previous experience that it's probably minus B transposed. Let's pursue idea 2, it's equilibrium. So let's consider a 2D continuum. The region inside is called omega, the boundary is called gamma. There's a part of the boundary where the displacement is prescribed, we call that gamma u, and another part where traction is prescribed, we call that gamma t, and inside the continuum is external force P per unit area. Now out of this, let's cut out a region omega bar with boundary gamma bar and draw a free body diagram. So there are the forces inside and the tractions at the boundary of this cutout region. So if we do sum of the forces, we get the integral over the inside of p hat plus the integral over the boundary of t equals 0. Now this, just for comparison, we'll write the bar equation, which is the integral from 0 to L of p hat plus the tractions at the ends, as we've seen. So there is an interior component and a boundary component in both the 2D continuum and the bar. Now for traction, we can substitute sigma times n, which is the definition of the stress sigma. In the bar case, the next step was applying the fundamental theorem of calculus. The corresponding idea to apply in the 2D case is called divergence theorem. So we'll look at what divergence theorem is before proceeding further with this equilibrium equation. So let's say that we have a two-dimensional region. And in this region, there is a vector field called V. This could be, for example, a velocity, that's water flowing in this region, and the velocity vector field of the water is V, for example. Now, divergence from Calc 3, for example, if you remember, is defined as dvx by dx plus dvy by dy. And what the divergence theorem states is the integral over the boundary of v dot n, where n is the unit normal vector field, equals the integral over the inside of the divergence of v. So the meaning of the boundary integral is the rate at which water leaves the region, and you can see why that interpretation makes sense. Now coming back to our equilibrium equation, to turn it into a form that we can apply divergence theorem to, we dot the whole equation with a constant but arbitrary vector q. So we dot the two terms of that equation by q. Then we can rewrite the integrals like this, basically taking q inside in the first case and writing as sigma transpose q the whole transpose times n, and we can identify the sigma transpose q with the v in divergence theorem. So now we can apply divergence theorem, where the first integral remains the same. Now the second integral, we've applied the divergence theorem. Now the vector field v is sigma transpose times q. The sigma is symmetric, so the transpose is the same as the matrix itself. So sigma times q can be written like this. So if we did the divergence calculations and collected the terms and so on, which you should do to make sure that you get the same result as this, we get something like this. Q transposed times whatever is in this parenthesis, integral of that equals 0. Now because the region we cut out omega bar is arbitrary, and the vector q we chose to do the dot product is also arbitrary, if that integral is 0, then the term in the brackets must be 0, which gives us these two equilibrium equations in the x direction and in the y direction, which we can write in matrix form like this. And this matrix connects sigma to P. So this is the missing leg in the Tonti diagram. So this matrix minus of this matrix of d by dx, 0 d by dy, and so on, we call B star, and we recognize that it is minus B transposed.